Welcome to the T324 lectures. In this lecture, we'll start explaining about digital modulation techniques. First of all, it's very important that you understand the Fourier analysis for being able to understand how we are representing the spectrum of the modulated signals later on. So here we are presenting a brief overview on Fourier analysis. You can find many other references that you can rely on for further understanding about this theory. Basically, a signal could be represented in the time domain as graphs against time, or in the frequency domains, in which signals are described in terms of their frequency content or spectra. So this is the key issue that we should understand in this part, is that how we can represent the spectrum of the signal and what does it mean. So basically, sinusoidal waveforms are fundamental building blocks for the study of signals in communication systems. So we are a sinusoidal signal could be represented as a sine function or cosine, and it's a periodical function that is characterized by an amplitude, a frequency, and a phase. So if we would like to represent the spectrum of a sinusoidal signal, one could obtain in the graph of amplitude versus frequencies one single point, since we have in the sinusoidal signal one single frequency and it has an amplitude. So any sinusoidal waves will have the spectrum representation of any sinusoidal wave is a single point in the spectrum graph. If we take an example of the summation of two sinusoidal waves, so we can obtain some periodical function, as you can see in the following figure. And if we want to represent this periodical function in the frequency domain, so we will have 2 points that belongs to two different frequencies, and for each frequency we have its proper amplitude. So the summation of two sinusoidal waves will provide a function having 2 points in its spectrum. And if we continue in this way, so if we make the summation of 3 sinusoidal waves, we will have a periodical signal that has 3 points in its frequency domain representation, and so on. So to generalize with the following rule, so we can say that a periodical signal is one which repeats exactly and indefinitely with a constant repetition interval or period t. So any periodical signal f of t can be modeled to any required degree accuracy as a Fourier series of sinusoidal components. So where the fundamental angular frequency of the Fourier series is related to the period by the well-known function omega equal to pi over t, or equals to pi f. So any periodical function could be represented by the summation of a set of sinusoidal waves. So these representation facilitate the frequency domain representation of f of t, where we could have, in this case, if we have n sinusoidal signals as components of the periodical function f of t, then we will have n frequencies represented in the spectrum of the signal. So you can read these examples that could help you to better understand the Fourier analysis after explaining its major concept. The following figure shows the sum of a finite number of terms up to and including the ninth harmonic of the Fourier series for some standard waveforms. The limitation to 9 terms means that the approximation is still quite raw in the case of the square wave and S1to4 wave, whose higher harmonics are still of significant amplitude. However, in the case of the triangular wave, whose higher harmonics rapidly becomes very small, the approximation to an ideal triangular wave is very good. Now we're going to start with the basic modulation techniques. We will consider in this course only the digital modulation, and analog modulation will not be tackled. So basically two practical problems in radio transmission are how to get the electromagnetic radiation to carry the data that needs to be transmitted, and how to prevent each transmission from interfering with all the others that might be using the same part of the electromagnetic spectrum at the same time. So the solution is the modulation. Supplies techniques for grafting data into electromagnetic waves, and it supplies ways of keeping separate all the many transmissions that might be happening simultaneously. So we need to transport data over a wave. This is the first requirement, and the second requirement is that we cannot handle data over the same channel, so we'll have interference. So data should be modulated or carried over the radio wave in a way that it should be carried over different frequencies, over different channels, so that we can manage the spectrum and prevent any potential interference. The two basic modulation techniques are the pulse method of modulation, and the second is the carrier wave method of modulation. As for the carrier wave methods, the starting point for carrier wave methods of modulation is sinusoidal electromagnetic waves, electromagnetic sine or cosine waves, or portion of them. These waves are used to convey data, but we should select the frequency, channel frequency appropriate to carry data over it. So in this case we can prevent any potential interference. So a sinusoidal electromagnetic wave used in this way is a carrier wave. Data is encoded into a carrier wave by modulation. During modulation, an electromagnetic wave is modified so that the modifications represent the original data in some way. There are many ways of modulating a carrier wave, and each has advantages and disadvantages. You can see in the following table an extracted data from standard of wireless communication, which is IEEE 802.11a. Here we have some specifications that varies, and it has different impact on the data rate. So at the end of this part of the course, we'll be able to see and to understand how the performance or the data rate of our wireless channel could be varied according to different parameters. One of these parameters is the modulation. How we can modulate a signal by changing its amplitude. Amplitude modulation is any type of modulation that uses changes in amplitude of the carrier wave to convey data. We refer to the signal prior to modulation as the baseband signal, as you can see in the following figure. Unmodulated carrier wave consists of a continuous sine wave of constant amplitude, the height of the peaks, and frequency. The carrier wave modulated to carry the data. So this is a carrier wave in part B, and this is the data that will be carried in part A of the figure. We have digital data. As we have said, we will not consider any other type of data. So we have, for example, here 0111, 000, 101. So for each bit has a duration tau. We'll consider that the bit duration is tau, and during this period of time tau, we should modulate the carrier wave, the sinusoidal wave that has the frequency of the channel in part B. We should modulate it in a way to represent the bit, whether it is 0 or 1. So during we'll have a symbol that should represent a 0 or a 1. Basically, we have on-off keying or OK, where the presence of the carrier wave represents 1 and the absence of carrier wave represents 0s, as you can see in the following figure. So in part A we have the digital data, in part B we have the carrier wave, and in part C we have the OOK modulation. For OOK modulation during tau, the sample period, is represented by absence of carrier wave to represent 0 and a full carrier wave to represent 1. In part D we have amplitude shift keying, ASK. In ASK we represent the symbol that represent 1 has a full amplitude, and the symbol that represents 0 has an attenuated amplitude. So on-off keying can be viewed as a special type of amplitude shift keying in this case, one in which 0 amplitude is used as one of the two potential possible amplitude states. Amplitude shift keying is itself a type of AM, amplitude modulation. Nevertheless, drawbacks of OOK are prolonged non-transmission might mean a prolonged sequence of 0, or that no message is being transmitted, so systems switch off. So how we can differentiate by non-transmission and transmitting a binary code 0. The second drawback is that it needs for synchronization between receiver and transmitter to work out how many zeros were sent. There is no need for such synchronization where one are transmitted, of course, because the carrier period is known. How to achieve ASK? Two sources of oscillations running in step by producing oscillations of different amplitudes. Switch between them as required by the data. Switching usually done at the 0 crossings for a small transition. Jump in amplitude is like a sudden pulse which generates a pulse of electromagnetic waves covering a wide spectrum of frequency. This leads to interference with other devices. So what you can understand by this? Switching usually done at the 0 crossing for a smooth transition. Jump in amplitude is like a sudden pulse which generates a pulse of electromagnetic wave covering a wide spectrum of frequencies. So we will see in more details about the impact of having a smooth transition in amplitude or sudden switch in amplitude. This has an impact on the spectrum of the modulated signal. So of course the wider the gap between the amplitude, the wider the spectrum of the modulated signal. And if we have a smooth transition between amplitude, in this way we can have narrower spectrum of modulated signal. In OK and ASK, the modulated carrier wave has two states or signaling state. OK, the states are wave present and wave absent. ASK, the states are full amplitude and reduced amplitude to represent zeros and ones, as we have previously described. So carrier states such as these are known as simples, and a simple has a duration tau. In modulating a carrier wave, we are not restricted to two symbols, and some of the modulation methods you will look to use many more than two. For example, if you take ASK, you can have, for example, 4 different symbols represented by 4 different amplitudes. And if we have 4 different symbols, then we can represent each symbol can represent, in this case, a combination of 2 bits. So the number of combinations of 2 bits is 2 power 2 equal 4, and we have 4 different symbols. So each combination could be uniquely represented by a symbol. So to generalize, if we have number of symbol n is equal to 2 to the power number of bits per symbol. So the number of bits per symbol is equal log base 2 the number of symbol. So the number of bits is equal log base 2 of 4 If we have 4 symbols, so it's equal to. If we have 8 symbols, the number of bits will be log base 2 of 8. This is equal to 3. So we have 3 bits per symbol in case we have 8 different symbols. In case we have 16 different symbols, this means that the number of bits is equal log base 2 of 16. It's equal 4, so we have 4 bits per symbol if we have 16 different symbols. And each combination of bits has a unique symbol that could represent it. And calculated 4,500 symbols per second times 4 bits per symbol. This leads to the number of bits per second. In this way we can calculate the number of bits per second, the data. If we take another examples, if we have a modulated signal that has a signaling rate S equals 6,000 volts, this means S equals 6,000 symbols per second. And if we are using 16 QAM, that uses 16 symbols, 16 symbols means 2.2 power 4. This means we have 4 bits per symbol. And if we have the signaling rate 6,000 symbols per second, then we have the data rate is equal 6,000 symbols per second times 4 bits per symbol. This means 24 kilobits per second. Another type of digital modulation technique is BPSK, binary phase shifting. Previously, I have seen ASK, amplitude shifting, where we change the amplitude of the carrier wave during tau to represent 1 or 0. Here, during tau, we should change for the phase of the carrier wave for representing 1 or 0. For example, one can represent the bit 1 as the carrier wave having the phase 0, and the bit 0 could be represented by a carrier wave having a phase that is varied by 180 degree with respect to the bit 1, or to the symbol that represent bit 1. So we have two different symbols that has the same amplitude and the same frequency, but two inverse phases. The one could represent the bit 0 and the other could represent 1. And in this way, the demodulator at the receiver side could differentiate after every symbol period tau if what we are transmitting, if it is the bit 0 or 1. Another modulation technique is frequency shifting, AFSK. So in ASK we change every tau the amplitude without changing the frequency and phase. We have seen also that in BPSK we are changing only the phase without changing the amplitude and the frequency. In AFSK here we will not change neither the amplitude nor the phase, but we will change the frequency. So one symbol having a frequency of 1 will represent a bit 0, and the another symbol having another frequency f2 will represent the bit 1, and so on. One variety of FSK is to use CP FSK, continuous phase FSK. In order to reduce the changes between symbols, and if we can reduce the changes between symbols, we can have narrower occupation of the channel spectrum. So if we can reduce the channel size if we reduce the changes between symbols. So here, for example, we are not changing the amplitude, we are changing only the frequency. So if we are changing the frequency to represent zeros and ones, and we don't need to change the phase for this purpose. So let's have continuous phase to reduce any potential changes in phase in this case. So continuous phase will help to reduce the channel size. So we will have, so continuous phase FSK is a better version or variety of FSK. So if we want to represent the circuitry of these three basic modulation methods, so in ASK we have an oscillator and an attenuator, and the message will be switched between the two different inputs. Every symbol duration tau will be switched between them to take the symbol which could have full amplitude or attenuated amplitude according to the binary input, if we have 0 or 1. As for BPSK, we could get the input from an oscillator when we have to get it in phase or in shifted phase according to the digital message input 0s or 1 every tau. And for frequency shifting, also we can switch between the input of the two different oscillators every tau to get the symbol with frequency f1 or f2 according to the digital message input as well. Another variety of phase shifting is differential phase shifting, DPSK. The issue is that the absolute phase of the signal is often unknown. Only relative phases can be identified. So DPSK can be described by the rules. If the data is 1, change the phase by 180 degrees, and if the data is 0, don't change the phase. The receiver then provides a 1 as the input if the phase changes between successive symbols in the received waveform, and a 0 if the phase is the same between successive symbols. The essential of differential encoding is to use a change of symbol or the absence of a change to represent data. In DPSK, we don't use a particular phase to represent zeros and another phase to represent 1. The presence or absence of a phase change at the end of a symbol period represents a data bit. Take the following examples. So we should, if we are if we have modulated the signal by the PSK, then we should know the symbol, the bit represented by the first symbol in this example, to know what is the bit represented by the first symbol. So if the symbol which is not drawn for the first time slot tau, so if it's in phase with the second symbol, so the one represented here in the second time slot is 0, and if it's shifted in phase, so it's 1. So let's start with the third time slot. In the third time slot, we have so here it is. In the third time slot, the phase is shifted with respect to the previous one, so we have a 1. And for the fourth time slots, we have the symbol which is in phase with the previous symbol, so we have 0, and here we have 1. We have shifted the symbol in phase, so we have also 1. Here we have also 1. Here we have 0 because it's in phase with the previous symbol. Here we have 1, here we have 0, and here we have 1. One variety of frequency shift keying is minimum shift keying, MSK. Binary frequency shift keying uses two different symbols, but how widely separated those two frequencies would need to be. There is a limit as to how close the frequencies can be. So if the two frequencies are if we have a large gap between the two frequencies, this will lead to a wider band in the modulated signal. And if the two frequencies are too close to each other, then we have the risk of having inter-symbol interference. So what is the trade-off, or what is the minimum shift keying required for selecting the frequencies of the two symbols in this case? It turns out that there are particular advantages to using pairs of symbols which differ by an integer number of half cycles of a sinusoid. So the minimum shift in frequencies is equivalent to a half a cycle of sinusoid. The smallest frequency separation for which this can be the case is when the symbol using the higher frequency contains just 1/2 a cycle more than the symbol using the lower frequency. We can derive a formula relating the frequency spacing f2 minus f1 to the signaling rate as if there is half a cycle more at the higher frequency f2 than the lower frequency f1 during one symbol period. The minimum frequency spacing is numerically equal to half the signaling rate. So if we want to calculate the shift in frequency based on the minimum shift keying principle, which is half a cycle, then one can say that we have f2 times tau, the number of cycles during the symbol duration tau, minus f1 times tau, which is the number of cycles during the symbol duration tau for the first symbol. The difference between them is 0.5, half a cycle. The difference between the number of cycles of the two symbols. So f2 tau minus f1 tau equals 0.5. This leads that f2 minus f1 is equal 0.5 over tau. This leads to 0.5 s, since signaling rate s is equal 1 over tau. We can obtain in this case the formula for minimum shift gain, which is f2 minus f1 is equal to 0.5 s. A modulation scheme with these parameters, CPMSK with a frequency spacing of 0.5 s, is called minimum shift gain. What about the reception of the modulated signal? Selecting the transmission associated with a single carrier frequency is essentially a filtering operation. You can imagine filtering as opening a window or passband on the frequency spectrum. Frequencies within the passband are allowed through. Frequencies on either sides are rejected. But the problem is not as simple as that. So let's look to the following figures. The figures show hypothetical signal strength emerging from the tuning part of a receiver. Strength is greatest in the center frequency of the passband Vmax. The signal strength in the passband gets way weaker at frequencies away from the tune frequency. We can define a fraction V over Vmax which has a maximum value of 1 at the tuned frequency and falls away on either side. So it's not a square function around the tuned frequency, which is the channel frequency, but it's an hypothetical form. Okay, so how to solve this problem? This fraction is called the response of the receivers. So how we can filter the received signal based on the response represented in the first part of the figure. So if we make the filter according to the figure B, the receiver responds narrowly to the tuned frequency, but the response rapidly drops off away from that frequency. A response like this not properly capturing a transmission that is spread widely around its carrier frequency. The other option is represented in part C. In C, it shows a wider response, but this is too wide and it risks picking up other transmissions and noise. The response of the receiver ideally should match the spread of frequencies in the transmission. So how to solve this problem? We define the passband as the following. By convention, by the time the response has dropped to 0.707, the edge of the passband has been reached. The frequencies which mark the limits of the passband are called cutoff frequencies. So we take the maximum response value from the top one till the edges 0.707, and we will have from one side the lower cutoff frequency, this response value, and from the other side we will have at this response value the upper cutoff frequency. The origin of the number 0.707 lies in the use of decibel scale. The response at the cutoff points is 3 dB, 3 decibel below the maximum value. 3 decibel correspond to the amplitude ratio 1 over 0.707. In this way, the concept of a cutoff frequency allows a more precise definition of the bandwidth of a signal or channel. The bandwidth is the difference between the upper cutoff frequency and the lower cutoff frequency.